I'm Oybek Kolikoff.
JJ Katz.
Daniel Millstone. Daniel Millstone. Daniel Millstone.
Throughout the lab, we needed to find the distances between different optical components. Because we didn't care about the exact location of each component and rather about the distance between them, we used the microscope approach, in which we took the microscope, represented here by this marker, and focused it on an object, say for the first part of the lab, the laser surface of the cavity. We would then move it backwards to some amount, and for the first part of the lab we used a knife edge, and we put it there and adjusted it until it was in focus. The distance that the microscope moved, which could be exactly measured, was the distance between the laser surface cavity and the knife edge. So in the first part of this lab, we used a laser without a lens, and that served to put the beam waist right at the laser cavity surface. From there it started diverging. We moved the knife edge about 1 meter away and scanned it across to create a beam profile. Then we moved the knife edge another arbitrary distance, which we then measured, and then took another profile. For the second part of the lab, we inserted a lens just after the laser. Technically, that lens performs a Fourier transform on that Gaussian distribution, creating a scaled Gaussian distribution and an effective second beam. For that second beam, the beam waist is moved out further, allowing us to take a profile before and after. So the reason moving the beam waist is important is because the two distances used in our algorithm, Z1 and Z2, are measured from the beam waist. So if we move from the beam waist this way, it's technically negative. And if we move from the beam waist this way, it's technically positive, which gives two different results in our algorithm.
Oybek is using a micrometer to get precision intervals of knife edge position. The power at each interval is read out here. The collected data gives a beam profile. Let's pretend that this is a Gaussian distribution of our laser beam. Now in the lab setup, as we pan our knife edge across, this is actually a representation of what the detector might see.
The beam has a Gaussian distribution, so over at W2 when we took it, we expected the profile to have a more gradual slope, whereas when we took the profile at W1, the beam diameter is smaller, so we expected the beam profile to have a steeper slope. If we take them somewhat equidistant from the beam waist, we're going to see that the two profiles are roughly the same size and have similar slopes, yet not exactly the same.
86% of the beam power is contained within the beam waist between 13.5 and 86.5% shown here in green. The Gaussian beam diameter is within 1 standard deviation of the maximum beam irradiance and is shown in pink. The beam's irradiance distribution is similar to that of the error function in that its density is greater near the center. Without a lens, we can expect to see a narrow beam diameter at position E1, which is closer to the laser cavity. This is indeed the case, as we can see that the beam diameter is 0.72 mm close up and 0.85 mm at a farther distance. The Gaussian diameters are shown below the beam diameter. With a lens, if the knife edge is placed at the right location, both before and after the beam waist, you can obtain the same diameter. We chose an arbitrary placement and found values for the beam diameter at positions to the left of the beam waist being 0.66 mm and to the right of the beam waist being 0.127 mm.
Oybek, what are you working on?
The beam profile algorithm.
Can you show me how it works?
Of course, Daniel. So we have two cases, the case with the lens and the case with the no lens. I took the two data points that you gave me for the beam waist at the two different locations for both cases. We have our wave number in both cases. We have delta z, which was measured in lab, and we have this parameter of b. We then solve for this enormous equation and find the two roots. Then, by process of elimination, we find which root corresponds to our Rayleigh range, which is displayed here for both cases. We then can calculate our beam wastes for both. We can then calculate z1 and z2 for both cases. Do you get it?
Sort of, but what do those numbers mean?
Let me explain, Daniel. Here, let's take both cases with the no lens and with the lens. In the case with no lens, the beam solely just diverges all the way. So we have this enormous Rayleigh range and a fairly large beam waist at 0.5 mm. For the case with the lens, the beam goes through this lens and converges into a point and diverges again. Therefore, our Rayleigh range is much smaller at about 2.6 centimeters, and our beam waist is even smaller at 0.07 millimeters.